Hello, this is Paul from Tech. This video, let's prove the Theorem 2.3.3. This is an important theorem. We call it the Determinant test for invertibility. Okay. Later, these results were added to the Equivalence Theorem. The theorem says if a square matrix is invertible, equivalent to the determinant is not zero. Okay. If you see determinant is zero, definitely is not invertible. Okay. How to prove it? Let's look at two ways, because this is a equivalence if and only if. So let's prove at part 1, which is A is invertible. Can we find the determinant equals 0? That does not equal 0. Sorry. Why? A is invertible, determinant should be not 0. This part is quite easy. All we need is the equivalence theorem. Can you see? So first, A is invertible, and then we know A is a product of elementary matrices. A equals elementary matrices, whatever I said, E1, E2, to whatever EK. And all the E is elementary matrices. This is all elementary matrices. And so we do have this result from the equivalence theorem. You can look at it as 1.6.4. 1.6.4. Equivalence theorem is the most important theorem in linear algebra, right? So, and then what do we get? So easily we can get the determinant. We can calculate determinant of A should be the determinant of E1 times the determinant of E2. And here we times the determinant of the last matrix. We just proved, right? So, and the llama 2.3.2, or you say is a little bit generalized version of this llama. The product can break down into the product of determinant. And this way, can we see? Determinant definitely is not 0, because each one is not 0, right? So this is elementary. This is not 0. This is not 0. Each one is not 0. Therefore, the product is not 0. Yes, great. So the first, this is true, right? Okay, and then we backwards. Backwards means if a determinant is not 0, can we prove A is invertible? Yes, let's see second part. We say part 2. If a determinant of A is not 0, can you prove? Okay, matrix A is invertible. Yes, we do. But how? We still have to use the equivalence theorem, but this time I will look at the reduced row echelon. Remember that. So we can start from this. We can think about a reduced. Just let's R be the reduced row echelon. matrix of matrix A. So R is the reduced row echelon. Because A is n by n. Imagine A is n by n is square matrix. And then we do have a theorem before we learned for any square matrix, we have a property for the reduced row echelon. Only two cases. The first case, R equals identity matrix. If R is not an identity matrix, then R should be has one row on the bottom or zero, right? So can you see it now? We know, see, either okay, R equals identity of cos n by n, or zero. We simply say all zeros on the bottom row of R. And you can check. That's the theorem we learned for 1.4.3. So we just use this, and then based on the result, the determinant is not zero. I can determine reduce the row echelon should be identity. Okay, why? So I can say this is wrong. Okay, all zero on the bottom row. This is wrong. Why? Okay. Therefore, if this is wrong, I can get R. The reduced row echelon is identity, and then back we can use the equivalence theorem. We say A is invertible. But why? We still use the lemma. Okay, we just have. See, determinant of A. Reduce the row echelon. We know. Okay. R is the reduced row echelon means A left times row elementary matrix, a sequence of row elementary matrix. This E is different from the elementary and the first part. Keep in mind. Should be goes to reduce the row echelon, and that's a row operation, right? So this is a row operation, and all this E is a row get. This is elementary matrices. Okay. By this way, and then A is determinant of A is not zero. See, so determinant of R should be not zero, right? So therefore, from here, so we can find determinant of R should be equals determinant of each elementary times together. Determinant like E1 and then times determinant of A. See, and this is the previous lemma we learned 2.3.2. Okay, so because each determinant is not zero of the elementary, A is also not a zero, so therefore this is not a zero. This is not a zero means what? Means we have no or zero on the bottom row of R. You see, so therefore this is true, right? Okay. So we can get the bottom row. The bottom row of R should be not all zeros. Why? If it's all zero and then the determinant should be zero, but now determinant is not zero, so that's not. Therefore, we back. So you think about it, the original either or. So therefore, we do have R reduce the row echelon should be identity. Okay, and then by the equivalence again. by the Equivalence Theorem. Again, is 1.6.4. Again, A is invertible. That's the proof. Thank you.